do that. Okay, so first lesson of the semester. Remember last semester we only got through triangles. We are now going to go to all other types of polygons. The basic polygon we're going to work with in chapter 6. If we've gone from triangles, guess what we're going to go to next? Quadrilaterals. I know you're all profoundly moved by that. Actually, it's kind of cool. We're going to learn a lot of properties, really apply them to the point where we have them. A lot of definitions and memorizations this chapter, okay? They're not hard. You just got to make sure that you know them. Are you guys good with that? All right, so a few things you need to remember about polygons. Remember, the polygon I have drawn here for you is in red. And remember that each segment that forms a polygon is just called, this sounds real profound, I know, it's just the side of it, right? So we have the side of a polygon. Obviously, where a common endpoint of two of the sides is always called a vertex. Has that changed anything that we know before either? Nope, so we have a vertex. When you name a polygon, remember you have to name it either clockwise or counterclockwise and always in order. So like if you were to name this one, this would be polygon, we'll give it a more specific name in a moment. You go A, B, C, D, E. But if I don't like it, I could stop at a different vertex as long as I go clockwise or counterclockwise in consecutive order, which means one after the other, you'd be fine. Don't go A, B, E, D, A, C or something like that. Don't hop around. You have to go in order when you name it. Sounds good? Yes, ma'am.
So you can go A, E, C.
Yeah, you can totally go A, E, D, C, B. Because remember when we do geometry, it's connect the points. Like you start it and the order it tells you how to connect it. Even when we do angles and stuff. So we're just maintaining that when you work with it. We have a new term that we need to talk about, but it kind of makes sense. It's called a diagonal, okay? What is a diagonal? Well, a diagonal is another line segment. In fact, it's what's drawn here in green. A diagonal of a polygon connects what's called non-consecutive vertices, which means ones that aren't joined by a common line aside. So like here you'd have a diagonal, like right here's a diagonal. See if I can get it to draw. So this is a diagonal right here. Could I draw a diagonal from A to D or A to C? Yeah, so I could draw lots and lots of diagonals when you work with it. In fact, we're going to use that later to actually talk about measures of angles. So understand when I talk about a diagonal, it's inside segment. Sometimes it can be outside though. This is where I'm going to throw you off just a little bit. Okay, it can be also drawn on the outside as long as it's connecting to non-consecutive vertices. All right, let's see if you remember this way back from grade school. We know a polygon has to be a closed figure, correct? What was the smallest closed figure you can have? Triangle. So with the number of sides, we call it, of course, a triangle. When we have 4 sides, what do you call it? Yeah, quadrilateral. You are going to have to know these names now. But a lot of them you already know. Like, what do we call a 5-sided figure? Pentagon, right? I always like this because it always makes me think military, like the Pentagon. You know why they use the Pentagon shape? When there's an attack on the Pentagon, it can only get one portion of it. That's why when the airplane hit it during 9/11, they could still use the rest of the Pentagon. So it's a neat engineering feat what they used. What do we call a 6-sided figure, guys? Remember? Yep, it's a hexagon. What do we call a 7-sided one? This one actually has 2 names. It's called heptagon or septagon. You're going to hear it both ways, so you're supposed to realize it's both ways. I think your book might do heptagon a little bit more, but honestly, I will use both. It's one letter. Just know they're going to change it up on you. Obviously, if you didn't know this, I'm concerned. 8-sided figure. You have your octagon. 9 makes me feel like we're not talking about anything. It's called a nonagon. 10, close, pretty close, decagon. Still the stars, still the deci, D-E-C. Yep. All right, notice if you skip 11, there's a fancy name for it. You'll never use it, okay? You'll just never use it. A 12 would be a dodecagon, right? Do means how many? 2. So we're going to do a dodecagon. And here's the cool part. If you literally froze on a name, please don't do this on a test because I probably wouldn't give you credit for it. Like, mathematicians are lazy. So what if I wanted a 20-sided polygon? Because you can draw one. You you call it a 20gon. Now, does it have a fancy name probably besides that? You just don't have to use it. You just go, oh, look, a 20gon. How about 18 sides? Oh, it's an 18gon. 1,000-side figure. 1,000gon. They're lazy that way. So a triangle would be a what? Let's just say we still have way smarter than a triangle. But, you know, I mean, that's the type of stuff. Mathematicians take shortcuts all the time. Are you expected to know this? Would they expect you to know this on a standardized test? The answer is yes, 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 and yes. All right, so you've got to decide if something's a polygon or not. And remember, a polygon is a closed figure. So, and it's not going to overlap. So like on the very first one here, is that a polygon, even though it looks like Dracula teeth? Yeah, because it is a closed figure. Okay, here's my question. We know it's a polygon. How many sides does that have? If you count it, I got 1, 2, 3, 4, 5, 6, 7. Isn't it nonagon? So it's, yes, it's a nonagon. Now, how many of you have ever thought of a nonagon to look like that? But it is. But it is. All right, is B a polygon? The moment you saw that curved shape, could I use it? No, so that one's a no. Okay, you have your curve. It's not a polygon. So put a big no there. All right, how about the next one? Is that a polygon? What made this figure not a polygon? If you got rid of those two extended line segments, would I then have a polygon? But because they just extend out like that and they're not sharing a common endpoint, it's not a polygon. Now, is there a polygon within that figure? Yeah, do you guys see the quadrilateral that's there? It just can't be, the whole figure is just not a quadrilateral. Remember, just the quadrilateral, see if I can get this to work a little bit. This is a quadrilateral, but because I have those two extensions, I can't call the whole thing, the whole big figure, a polygon. So can polygons make up other shapes? Yes. But just remember, if I'm looking just for a polygon, it's not going to be there. All right, some other terms that you have to know. Guys, you know how this class is so heavy laden with terms? Guess what? They don't go away. And that's the type of stuff that's really hard. Like the number one reason international students struggle on the math portion of an ACT is not because they don't know the math. It's because the vocabulary is hard because it's in English. So for you guys, you're lucky it's in English, but you still just have to memorize the vocabulary for this. And some of this is very, very common sense for you. Like for instance, what would you call a polygon if all the sides are congruent? Think triangles. What would you call a triangle when all of its sides were congruent? Yeah, equilateral. So any polygon that's all of its sides are the same, it's going to be equilateral. What if I have when all my angles are congruent? What would we call that? Again, think triangle because it's easy to way to memorize. Exactly. Equiangular. Does a polygon have to be both equilateral and equiangular? Only time that has to happen is a triangle. The rest of the time, you can be one or the other. Now, this term is actually the one that shows up a lot, and we really need to make sure you know. It's called a regular polygon. It sounds like it's just out on the street corner and anyone wouldn't recognize it, right? A regular polygon is a polygon that is two things. It's equilateral and equiangular. Well, obviously with triangles, that's really easy. We already knew that an equilateral one was equiangular. Can anyone tell me what the equilateral, equiangular, quadrilateral is? Your square. So if you have a regular quadrilateral, you're just talking about a square. So it's the same type of idea. Could you have the same idea with pentagons? Yeah, a regular pentagon is all the sides are the same. It's like, I always call it the pretty shape. It's so symmetrical. It's just so, works out really well. Everything's the same. All right. If a figure is not regular, you're going to be calling it irregular. I know, profound vocab. Irregular. Or not regular. Wow. When we also work it, we have two other things. You guys, have you worked with the lenses yet in physics? Like bending light or anything? Okay, or like concave mirrors. Sophomores, you know what I'm talking about a little bit more. Concave or convex. We use the same terminology in math. Freshmen, give yourself about a month. Okay, and you're going to get it in physics. All right, but polygon also has two different types of shape. One of them is going to be concave. What does that think about? When you see a cave, what does it do? It goes inside, right? So think of a cave-in when you know it. A concave polygon is a polygon if any part of a diagonal contains points in the exterior of the polygon. Let me show you what I talk about right here. Do you guys see the concave polygon down below to the left? Do you see it's just a quadrilateral, right? Do you see how it looks like it's got pushed in, caved in? Look at the diagonal that's in being dashed just to show you the difference. Remember, a diagonal just connects non-consecutive vertices. Did you notice the diagonal's on the outside? So if any part of this diagonal right here is on the outside, that blue dashed line is on the outside, you know it's going to be concaved. It's an easy visual. Is it caved in or not? So that lovely nonagon way on the top of the page, is it going to be concave? Is that concave right here, guys? Yeah, that's going to be concave. That's the type of terminology they're using. Does that make sense? All right, so concave is caved in. If no diagonal ever goes on the outside of the polygon is called convex. Most of the time, but not all the time, we use convex. And a regular polygon, and this is where it's going to be key, a regular polygon is always convex. So that's one reason why we use convex and regular polygons a lot. They're easy to use. It's very easy to see those figures, very easy to identify the type of polygon that you're going to have. All right, so example 2 here. Again, I told you we had tons of terminology today. It says, name the polygon by the number of its sides, then tell whether the polygon is regular or irregular, concave, or convex. All right, so the very first one, let's kind of go backwards. Is it concave or convex? Which one is it? Yeah, this is going to be concave. Is it regular or irregular? Irregular. Now name what type of polygon it is for me. Yep, it's another nonagon if you count the sides. And I don't know about you, but when I do something like this, I actually physically have to write it. Or I'm a really bad person for teaching math. Counting, I miss numbers all the time. Don't know why. So, concave, irregular, nonagon. Make sense? All right, how about the next one? What type of polygon is it? This one should be quick. What is it? Quadrilateral. It's just 4 sides, guys. Quadrilateral. Don't overthink it. All right, so it's a quadrilateral. Is it regular or irregular? All right. It is equilateral. You guys agree with me on that? Yeah. But is it equiangular? No. So in this case, it's going to be irregular. All right, now is it convex or concave? Convex. There's no way if I drew a diagonal, right? Would that ever come on the outside? No, not on that one. So excellent. All right, how about C? What type of figure is it? Quadrilateral. I bet most of you would name it more specific than that if I didn't have the fact we just talked about quadrilaterals down. Most of you, would you have called it a square? Thank you. All right, good. So quadrilateral. If it's a square, it means it's what? Regular, irregular? Yep, it's going to be regular. And remember, if it's regular, it's automatically what? Convex. On D, what type is it? It's a quadrilateral. Isn't that mean I put 3 quadrilaterals in a row to make it to do this? So I had quadrilateral. But in this case, we know it's concave, right? And is it regular? No. Again, it's going to be concave, and it's going to be irregular. Guys, just noticing that type of terminology and stuff, it's not hard. Can you see how easy some of your homework problems are going to be? Rough day in math class. All right, let's keep on going. E. What type is E? 5 sides, so it's what? Pentagon. Okay. Regular or irregular? Right the way you saw it caved in, it's going to make it what? Irregular, right? And since it's caved in, that should be a U there. We know it's going to be concave. All right. Let's have some fun. How about F? What is it? Octagon. You guys, a lot of you know Cora, my daughter, right? Who's you're younger than most of you, or 2 years younger than you. When she could barely speak, she was going around pointing out octagons to me. And I'm like, people are going to think I forced you to do it, kid. I was like, it was her daycare taught her. And so she'd go around and go, oh, look, that's a crescent. Like a moon would be a crescent. I'm like, every time I teach this lesson, I just remember her being a cute kid telling everything what's an octagon. It was wonderful. She can do it. Let's put it that way. She has to work hard. Some of you would say the same thing about yourself, like you can do math, but you have to work hard at it. That's more her. The work hard part is something she's working on. I'm waiting to see if I teach her next year or not. I don't know if I'm going to be her teacher or not next year. She's been accepted. Her placement test is going to be the tell-all. All right, anyway. Mean to me, I know. Sorry. Sorry, Cora. You'll probably see this someday. All right. G. What is it? Heptagon. Or could you call it what? Now, I'm probably only ever going to put one name down. So if you put septagon or heptagon, I know the difference. It's okay. Either one's fine. Septagon just sounds cool. All right. It just sounds good, doesn't it? I have so much fun right now with this. All right. Is it going to be irregular? Yep, irregular. And it's what? Convex. I totally forgot to write my stuff down here. Convex. Concave. Oh, that moved down. I copied and pasted it without meaning to. All right. Irregular. All right, we're all good. All right, so far we good, guys? All right, the next one is as good as I can do. Description is, you all know the measure of the angles of a triangle. What do they add up to? 180. Can I just remind you, so you don't do this on a silly error, the sides of a triangle don't necessarily add up to 180, right? Angle measures add up to 180 degrees. One of my biggest pet peeves is watching people mark angles on the sides, okay? Don't do that, or vice versa. But we know that the measures of these angles add up to 180 degrees, right? Guys, most of you know the next one. What did the measures of the angles of a quadrilateral add up to? 360, because if you think of a square, right, you go 90 plus 90 plus 90 plus 90, it's 360. How in the world did they get that? It's the fact that, those things called diagonals come in handy now. Because can I draw a diagonal in from the vertex? How many triangles do you make? 2. Well, can I figure out the measures of those angles? Could I add them together to add up to be the angles of the quadrilateral? Right? So look what happens down here. We can easily make a pattern with this. Like for a triangle, I have one triangle, and I want to find the sum of its angles. It's going to be 180 times 1, which is 180. How many triangles do you get when you have a quadrilateral? Yeah, 2 times 180, right? It's going to be 360. Now, and here's the other thing. I'm using what type? I'm using a convex, okay? I'm using convex polygons. A pentagon, if I draw the diagonals coming just from one vertex, how many triangles do you get? 3. What's 3 times 180? If you guys do that in your head, I'm so proud. What is it? Yep, 540, right on. So 540 degrees. Guess what? You have no excuse for not knowing what's the sum of the angles of a pentagon now. 540. All right, a hexagon. How many triangles am I going to draw with a hexagon? You got 1, was it 1, 2, 3, 4? So 4 times 180, isn't that 720? All right, do you think there's a pattern here? Notice when I draw it in, I'm using the pattern being drawn. The number of sides I'm going to call n. By the way, n a lot of times is just always the number of sides. The number of triangles I get if I draw the diagonals from just one vertex is always 2s. Did you notice that? So it's n minus 2. So if I don't know, let's just say I had a 100-sided polygon, I'm not going to sit there and do a long column and pattern. I want to be able to have a formula that allows me to figure it out. It's going to be n minus 2 times what lovely number? 180. And in fact, that's your next theorem. We just discovered it. It's called the polygon. Okay, are you ready for this? Angle sum theorem. We're adding up the sum of the angles. It's a profound moment, I know. So the sum of the interior angle measures of a convex, this is the key word, convex polygon, with n sides is just n minus 2 times what, my friends? 180 degrees. That's all it is. So is a calculator nice with this? Would you write this formula down even though it's really easy? Some of you are like, no, I can just write. Just do. It'll help you memorize it. Show your work with this one. Because look how easy this really is. It says, find the sum of the interior angle measures of a convex Levengon. Well, what's n going to be, guys? Yeah, n is going to be 11. So can't I just write my formula down? N minus 2 times 180. Go 11 minus 2 times 180. So I'm showing my work. 9 times 180 equals what, my friends? It's larger. Calculators are helpful here. All right, you shouldn't have to have one. What's 9 times 0? 0. What's 9 times 8? Carry the 7. 9 times 1 is 9 plus 7 is? Yes, I just put it, literally I did the chalkboard in my brain, all right? I literally did the chalkboard like when you're a kid multiplying. This is what I did. So you can't get it. So it'd be 1620. The same type of idea with a 14gon, okay? Guess what we're not going to do it for? 14gon. I think you guys can do it on your own, okay? This next example, I'd make sure I pay attention to. It says, find the measure of each interior angle. Now notice it says each interior angle of a regular 18gon. Help me out, people. How can I find an interior angle of a polygon? Find the sum first, right. So exactly, I'm going to find the sum first here. I'm going to go n minus 2 times 180. But what would I have to do to that sum? Divide it by the number of sides, right? So really, could I use this as a formula? Notice I didn't put the 18 in. I need to know first the sum of all the angles, but because I know it's a regular polygon, I know all the angles are the same. Can I just, number of sides and the number of angles are the same thing. So can I just divide by n? So can I just plug it into this and figure it out? Yeah, you guys did a great job figuring that out. So 18 minus 2 times 180. Now, for those of you who are like me, wouldn't that be a fun thing to do on your fraction key on your calculator? Wouldn't that just save a lot of work? You don't have to do any simplifying then. Even though you should get on there, it'd end up being 160 degrees. It's actually pretty simple to simplify in your head, but 160. Now, that only works to find one interior angle if you know it's a regular polygon. Make sense? So make sure you read carefully. On the next one, it says find the measure, make that a little bit smaller, of each interior angle of a hexagon A, B, C, D, E, F. All right, I want to know the measure of each one of these. How am I going to find that? Yeah, I'm going to have to find the sum first. So let's do that real quick. N minus 2 times 180. Let's go, what do we got? Hexagon, so it's 6 minus 2 times 180. What did we calculate that on the other page to be? 540? Someone double check me. Oh, 720? Yep. Oh, right, you're right. It should end up being 720. All right, so 720 degrees. Now can I just do sum of the parts equal the whole? The sum of all the angles should equal the whole amount of their sum. So literally, could I just go, and this takes a little bit of time, but 5a plus 4a. Here's the hardest thing. What if I don't want to double count anything? So you kind of need to know where you start and where you ended. And I want to make sure I only have 6 angles. All right, if you combine like terms together, I get 9, 14, we got 22. What did you guys get, 24a? So I get 24a is equal to 720. A is going to equal what, my friends? Yep, 30 degrees. Awesome. All right, now I have to plug and chug it in. Let's plug and chug and see if we can keep this as easy on ourselves as possible. The measure of angle A, is that just 2 times 30, so that's 60? Are B, D, and F all the same thing? Here is how I'm going to make sure I get all those answered. Let's say they're all equal, and just go 5 times 30, which is 150 degrees. Measure of angle C is just 4 times 30. I think that's 120. And then we have the measure of angle E. Guys, please use notation and what you know about math to your advantage, please. Use it to help you, like the measure of angle D equals measure of angle, D, all that. Put them all three there. Don't write it down every single time. Take yourself time. What do you guys think? Pretty easy? All right, I need you guys to go back with me again to something we did the other day. Do you guys remember what exterior angles are? It's when I extend one of the sides, right? If you extend one of the sides and you go in the same direction for all of them. So I want like an exterior angle here, 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 and here for a polygon. So like a pentagon would have, it has numerous exterior angles, but if I only draw one at each exterior angle, you should be able to find its measure, especially if I know the interior angle. It's going to have a really cool pattern. Those of you who have your calculators out, do me a quick favor and add all the exterior angles up on the first one for me. So that would be 111 plus 43 plus 110 plus 55 plus 41 equals 360. Do it on the triangle now. So that was for a pentagon one. I'm extending it now this time. 147 plus 81 plus 132. Think there's going to be a pattern? What if I had a 100-sided polygon? What convex polygon? What would be the sum of my exterior angles? A pentagon. Octagon. A 1,000-sided polygon. The sum of the exterior angle is always 360. Every single time. Isn't that kind of cool? So do you think we have a theorem for that as well? Yes! All right. Now, here's the thing you need to remember how to make that exterior angle. You only do it on one side of the polygon and you do only one per angle. This is kind of the key thing. But this is called, go figure, the polygon exterior angle sum theorem. Notice I can't say triangle because a triangle, we had talked about the two remote would add up to the exterior. This time it's just all of them. So we know the sum of the exterior angle measures of one angle at each vertex of a convex polygon is 360 degrees. All right, scholars, guess what you just did? You survived all the new theorems and notes. We just got to do practice problems. Anyone feel like your fingers ready to fall off yet? Welcome back to Geometry second semester. We go 100 miles an hour. Okay, this is normally a lesson I teach on a block day. Somehow we're getting through this. Are we good? All right. Now, let's go through and have a little bit of fun with this. Read carefully. The number one thing I told you guys, we got to work on the R word, right? Read. Okay, and here, make sure we're doing this. Let's read this first problem. It says, find the measure of each exterior angle of a regular 15 line. I want the measure of each exterior angle of a regular 15 line. Suggestions, anyone? You could draw it out, but I'm not going to draw a 15 line. I'm not really that good. What do you know about the sum of all the exterior angles? They're 360. But what do you know about all of them? Some of you are telling it to me. I'm not telling you you're wrong. Some of you are right. They're all the what? If the interior angles are all the same, what do the exterior angles all have to be? So could I just go 360 divided by n to get the exterior angle? Could I literally do that? Because now this only works though for what type? A regular one. So really all you have to go is, all right, 360 divided by 15. What is the measure of that angle? A couple, you've got your calculators going. 20 what? 24 degrees. Again, you can't do that unless you knew it was a regular polygon or they had a nice elaborate diagram for us to use. But see how we can just use what we know to get us there? Could I use that angle to figure out what one interior angle is? You could actually work backwards with this and say, oh, I know an exterior angle, and what do I know about my interior angles and my exterior angles? This is interior, you know, this is exterior. Aren't those a linear pair? If I know one, can I subtract from 180 to get the other? Use what you know. Use it to help you out. All right, let's look at the next one. It says, name the convex polygon whose interior angle measures have each given sum. All right, so this is sum of all the interior angles. This is a type of problem that I always call work backwards. Do we have a formula for the sum of the interior angles? Yes. So can I use it? Yeah, I'm here. I know this is n minus 2 times 180 equals 2,340 degrees. Can I just do algebra now and solve for the number of sides? Because once I know the number of sides, can I name it right? Correct? So when I do that, first thing I'm going to do, am I going to distribute the 180? What's easier? The easier thing to do is actually to divide by 180. Because you just get rid of it and you don't have to worry about the parentheses. So divide both sides by 180 first, guys. So go 180, 180. Here's where I want to see your work, though. Just don't do this in your head on your calculator only. So what's 2,340 divided by 180? 13. Add 2, n equals what? 15. So what are we going to name this one? I know there's a if you want to go online, find the fancy name, great. I'm just going to call it 15 gun. Okay. I got shunned by Mrs. Napier this year because I didn't know the fancy name for like 11 gun. I'm like, I don't care. It's not important in my subject. She goes, oh, you're a geometry teacher. You know, I'm like, move on. All right. But so if you want to be cool like that, go for it. But remember, you have physics homework too, so not just math. All right. 720, could we do the same thing for the next one really easy? Yeah, we'll just go, all right, n minus 2 times 180 is equal to 720. I'm going to divide both sides by 180, so I get n minus 2 is equal to 4. Oh, look, doesn't that make sense for what we did earlier? N is equal to 6, which makes it a hexagon. Not too bad, is it? All right, now the next one, it's kind of the approach that you're going to want to take on this, but I kind of like this, okay? It says here, it's a multiple step, but not hard. An exterior angle measure of a regular polygon is given. So what type of polygon is it? So what do you know about all your interior angles? Doesn't that mean your exterior angles are what? All right, you will not be able to finish this without looking at your notes. Are you guys good with that? Actually, if we got this far, I'm pretty pleased. I won't be surprised if there's questions on that on Monday. All right, you guys did a great job. I'm going to write this down so we have it. All right, Lauren, here we go. Our interior angle is going to be 180 minus this. And guys, this will be posted on. I'm just writing the rest of the problem out here so you have it. So 140. And so what do? We want to find the number of sides. Yes, please. All right, what's up? Oh, yes, I need to sign that for you. So sorry, Catherine. Hello. How are you doing? Thanks, sweetheart. All right. Thanks, Catherine. Hoping we weren't too boring today. You were pretty engaged. I appreciated that about you. All right. Yeah. See you. All right. Find.
Thank you so much.
You're welcome. What, hon? Yep. You too. All right, guys, let me know if anything crashes on your surface or something.
Okay.
Okay? See you.
Wait, is that one a nonagon? Like, is that right?
For which one?
That one.
This one? Yes. Yes, you got it right.
I think I did it differently. Yeah. I don't think so.